No. Okay, works.
By Étienne, Artigau from Montreal.
No. Okay. So I'll be presenting work that has been submitted in a paper just a few days ago on sub-Kelvin precision measurements in stellar temperatures. And usually when we think of effective temperature, we see it as a basic parameter of your star, just to understand it with radius and mass. And the very, very best absolute TF are usually made with interferometry. We could argue, but in spectroscopy. And here we're always, when we think of absolute temperature, of effective temperature, thinking of the absolute value. But I'm really going to discuss precise differential measurement in effective temperature. Okay, so we won't be talking about getting extremely precise measurement in absolute terms, but in changes in time series of the effective temperature of the stars. And as for radial velocities, and you'll see how we came to this idea of measuring very accurately differential temperatures, usually differential measurements are way more precise than absolute measurements, and I'll showcase that. So when you go back to how you measure velocities, just to give context on the flow of ideas that got us there, usually it's basically all the PRV methods boil down to one thing in the end. You have a noiseless of hopefully, or you presume noiseless template. You have one observation for a given ith pixel, and you basically compare the difference to your template with the gradients, basically the velocity derivative of your spectrum for that pixel, and you just look for an amplitude. So you say basically if you have a single pixel, you could get a velocity if you knew the difference for that pixel compared to the template and scale that by the derivative in velocity space. Okay, so here's an example where you have one observation and a template. They're slightly mismatched. As you see, there's a velocity difference. You project basically the gradient of that line onto the difference, and then you get the velocity. So we're going to apply the same idea, of course, on any quantity in the spectrum. So if you can find a derivative against, so for a given pixel, and of course you're going to sum it over all pixels in your spectrum, you can find basically a very, very accurate measurement of any quantity in differences in time series. So we'll do exactly the same thing. We're going to say we have a template, we have a mean observation of all our time series for a given pixel, and you just subtract your template, and then you just take a derivative against velocity or something else, and of course that something else is temperature in the case. That's interesting here. So we have a framework, a line-by-line framework that we developed in Montreal to do that projection against velocity, to measure velocities very accurately, and we just implemented the same thing against temperature. So basically, the best differential RV measurements are good to tens of centimeters per second, and at best absolute to 50 meters per second. And I remind you, and you may disagree, but the very, very best absolute temperature measurement at best are in tens of Kelvin, and I'll show how you can get sub-Kelvin differences in time series, and it opens a new door, a new window on stellar variability. So we gathered HARPS, optical. So if, for those that don't know, HARPS is one of the prime exoplanet PRV instrument. It's been running for nearly 20 years. It's a workhorse at ESO. We also gathered about 100 spectra of stars with HARPS and 45 with SPIRU. SPIRU is a precision radial velocity spectrograph in the infrared, so wide JHK band. We picked stars that are slow rotators, well-behaved metallicity, no low metallicity object, main sequence, and so on. We registered them, and we look at every single pixel compared to a high-pass spectrum, basically what you get against temperature. So here's a random line. I don't remember which chemical species, but it's a random line. You just take for that pixel, what do you have as a behavior compared to the high-pass spectrum, and then you can pass a fit. If you have a polynomial fit, you have a derivative against that fit. You know the derivative, you go back to the equation I showed, and then you have your temperature measurement. So for SPIRU, you're not going to take, or for any instrument, you're not going to take one line and say, okay, my iron hydride line is the best to measure differential temperatures. You take every single pixel, every single line, so we estimate at about 16,000 lines, and you do smart statistics to it. And basically, your spectrum changes by 1 part in 10⁻⁴, typically for 1 Kelvin, but you average that over all spectroscopic features. So well, we tried it, of course, and I'm going to present results. We had lots of suggestions, people saying, hey, you should try my favorite star. You should try to see turbulence or whatever. So we picked 4 cases. We picked 2 M dwarfs, one of the least active M dwarf in the solar neighborhood, Barnard star. So it's a thick disk. It's very inactive, it's very modest photometric variability. We picked an activity monster, a UMIC, one of the most active M dwarfs in the solar vicinity. We picked Epsilon Eridani because we found gorgeous sequences with HARPS. I'll show them. And then also HD 189733, where we have a transit observation, and we'll look at time variability of temperature with that. So here's the result. So we had a discussion on GP processes. Here you have temperature fluctuation in Spirou data over 4 years of Barnard star. And you basically have fluctuation on the mean temperature of the star at about the 4 Kelvin difference. And you can fit a GP. It's not obvious there, but you can fit a GP. You get a rotation period that's basically consistent with HST photometry, with residuals that are about at half a Kelvin RMS to that GP fit. So it recovers a published period. There's no new discovery, but it shows that even in the least active M dwarfs, the technique does work. So that was the hard one. Now, AUMIC, I love these posters. I hope you all love them. So AUMIC is an extremely active M dwarf. It's a young one. It has 3 or 2 or 4 planets, depending who you ask. Don't hit me at the coffee break if you published any number other than that. And it's been monitored extensively with Spirou. So we have long time series. We have spectropolarimetry, so we could look at temperature differences and magnetic fields. So here's the time series, basically yeah, but you see the error bars there. So you see the rotation of AUMIC. It's not that you guess that you see it. It is there at many sigma. And basically, we recover a period that is consistent with literature value. And even more than that, so we have the small-scale magnetic field that has been measured by spectropolarimetry. And we actually show that temperature fluctuation on the surface of this object anti-correlate very nicely. So you see the anti-correlation coefficient at 0.9. So basically, the fewer active regions on the star, the hotter it is on average disintegrated, which makes sense when you think of it, but it's actually another tool. So interestingly, that you don't need a spectropolarimeter to measure temperature changes, but you have an extremely good tracer of small-scale magnetic field here. So Epsilon Eridani, it's an object that's about half a gig a year old. It has a rotation period with differential rotation. It will be important later. It has a massive planet on a long orbit. It's convincing. I don't want to offend anyone, but its values vary between papers, which is always not a good sign. But anyway, and it had a very dense HARPS monitoring in late 2019. So nearly, not quite, but nearly 1 observation a night over 80 days. And here's the temperature of Epsilon Eridani. And here's the scale. This is not an error. This is 1 at the top and -1 at the bottom. And you see basically the rotation and evolution of spot on the surface of Epsilon Eridani with a residual to the GP at a fraction of a Kelvin, which is pretty crazy when I think of it. And when you fit a GP, of course, you get a period, and there's a differential rotation. And we actually can map the latitude of active region that contrasts in temperature on that star is plus or minus 50. No big discoveries. There are many stars at about 5,000 Kelvin that show spot at these latitudes. So it's not shocking as a discovery, but it demonstrates that we can map out, combining with other techniques, position of spots on an object. HD 189733, it's like poster child of transiting hot Jupiter. It has been observed with Spirou many times to do transit spectroscopy. Now we observe something during transit on short time series within hours, basically that is equivalent to the Rossiter-McLaughlin effect in temperature space. So when you think of it, here you hide a cold part of the star at the limb. The star will look hotter. You get closer to the center. You hide a hotter region of the star, it will look basically cooler and so on. And is it there? It is there with about 1 Kelvin difference. So that's just beginning of egress, beginning of ingress, end of egress. And you see that positive feature basically hiding one side of the star that is basically cooler, and the bottom and the top again and back in this time series. So we tried to fit it. If you take literature value of the impact parameter, it's 0.69, so that dip at the center is not deep enough. If you just trusted us, don't do that. You would basically fit an impact parameter of 0.5. It would be discrepant with everything that has been seen and fitted in photometry. So I'm not saying that everybody's wrong, maybe, but probably not. I'm saying that basically models that we use and basically with the mu are maybe not as accurate. So, okay, so naive models reproduce the overall behavior, but not the detail when you fit things exactly. So that's to be done. And we call it a fox effect. And now if I show you a little fox like ears and nose, you cannot unsee the fox when you see these curves. Okay, so you all know, so I'd like to call it the fox effect, but it's up to you. So the method is fully implemented in a line-by-line framework. So it's a framework we've been using at UDM for radial velocity. It's available. It works with all these instruments. And the method can be applied to any data set, big time series. I'm thinking there are Carmenes people up there. You have like a treasure trove of temperatures hiding somewhere. So it's open to basically reanalysis of existing time series. There's nothing new needs to be taken. That we have lots of PRV data, people looking for planets we could use and look at these temperatures. You do not need a meter per second stability because, of course, you're looking basically at line depths. So you could use Espadon, for example. But if you have meter per second, fine, but it's not compulsory. And yeah, so paper has been submitted. So hello, the referee, if you're in the room, I did the maths, it's probably pretty likely, hello. And we'll make it all available with the derivative spectra once the paper's cross fingers accepted. Questions? Yeah.
So the reason I think why you use this derivative as a function of lambda is because you sum the spectrum as lambda. So if you do this as a function of t, you need models, right? But my question is, in what respect is your results for your method different from the pure chi-square model comparison?
Okay, so the question is, the derivative, you would need models, and how is it different from fitting a model? The question is, we tried models, it does not really work, you need templates. So it's actually a section in the paper, I didn't want to get into that, but it's actually a section in the paper. You can use models, but especially for M dwarfs, there are lots of mismatching lines. So that's why we have all these, I'll go back, all these templates, basically, where you determine empirically the behavior of every single pixel in the spectrum with temperature of the star. And yeah, so you can use model, but it does a pretty poor job, actually. Yeah, so yeah. And yeah.
So, Chris Tinney, University of New South Wales. Now that you've got an apparently, allegedly independent way of coming up with magic Gaussian process noise parameters. Can you take those that are now independent of radial velocity and apply them as magic Gaussian process noise parameters to clean up radial velocity data without, so that you're not using the radial velocity data to imagine magic noise?
Yeah, so how can we use these GP outputs basically to clean up PRV data? It's exactly the purpose, the initial purpose of this, and it became something of stellar astrophysics, but that was a purpose. You could use, and we've looked at it, so we have gorgeous sequences on Proxima Centauri. I didn't want to put it because we're still working on it, and the FF prime, there's an equivalent of the FF prime RV filtering. Basically, if you have a spot coming into view, then you have the derivative of the flux time series. It's basically the derivative of that is your RV signal times scaling factor with another term for convection inhibition. And we want to do the same, and it works on Proxima, but that's ongoing work. So that's actually the purpose, the initial idea behind the method is an activity tracer.
Okay, I can see that there are plenty more questions.
There's a coffee break.
Great, good stuff. So,
Come see me.
thank all the speakers.
Yeah.
No announcements. Go enjoy your coffee break.